So do you always do a test flight after you've done some major maintenance, like an annual? Well, stick with us on FlyWire. We're going to go do a test flight on Charlie. We just got it out of annual, so we're going to go make sure everything's working right. First thing to do is do a quick engine run before you take off, because I changed the oil in the filter. Hopefully there's no leaks. Hey, I'm Scott Perdue, and today on FlyWire, we're going to do a maintenance test flight. In the Air Force, we used to call them functional check flights. After major maintenance, you go do a check flight and make sure everything's working the way it's supposed to be before you release the airplane to regular service. We just got the Charlie out of annual. We did a few things that we need to check and make sure they're operating good, like we changed the oil, looking for a leak or something like that, and other things. So anyway, it's just kind of a prudent thing to do. Do a quick maintenance check flight. Doesn't have to be long, just to make sure everything's working right. And we're going to do that here in a few minutes. First, I'm going to get some gas. Traffic, Bonanza 33 Charlie's taking active 17 and departing to the northwest of Moreland. Mixture prop, throttle 5%, cow 5%, turn set. Alright, here we go. Just test flight. We didn't have any oil leaks. So here we go.
Since I have trouble walking, talking, and chewing gum at the same time, I figured I'd fill in the dead zone while I'm flying to test the test profile with what I'm actually doing and why. The first airplanes didn't really have any instruments at all. It's all seat of the pants. That's where it came from. The comment came from. But as the airplane began being used for other things other than public demonstrations, it quickly became evident that the pilot needed to know some things about his environment. As uses for the airplane grew, the inaccuracies of those instruments began to demand solutions that only a dedicated crewman could solve. For instance, flight engineers were needed to monitor and control the engines. Radio operators were needed for outside communication. Navigators were needed to keep tabs on where the airplane was and where it was going. And World War I accelerated the whole process and the technological development, and also the need for more accurate instrumentation. The problem was how to make it accurate, and how can you tell that it is actually representing what is actually happening. That's kind of sounds weird, but that's true. Flying in clouds was an ever-present issue, and then flight tests began to be a serious part of aircraft design sometime in the 20s. Some of you might have heard of Jimmy Doolittle. He's famous for leading the B-25 Doolittle raid on Tokyo in World War II. But what you may not know is that Doolittle was an integral part of developing the gyroscopic attitude indicator with Sperry, and he was the first pilot to fly blind in September of 1929. And he had to have accurate instruments to do that. So how instruments and airplanes were tested and calibrated at first, how did they do that? Well, at first they did it over known courses. Test airplanes and pilots would do things like fly over a predetermined course real low to the ground and then record the time it took to make the flyover, or fly by a tower at a predetermined altitude. Later on, radar tracking became the standard, but for the most part, flight test engineers would spend a lot of time on a pacer aircraft. They'd test one airplane and say that this is accurate, the airspeed, the altimeter, all that stuff is accurate, and then they'd use that as a baseline to test other airplanes by flying in formation with it. What they began to discover was that accurate instruments are complicated things. There are all sorts of things that are different in the airborne environment. Vibration, temperature changes, humidity, pressure changes, all sorts of things affected an accurate reading. And have you ever wondered how many airspeeds there actually are? Well, maybe you remember from your initial training days, but airspeeds aren't complicated. First, you have indicated airspeed. That's what most of us use every day. We see it on the panel. Indicated only works basically when you're airborne or getting close to it. But IAS, indicated airspeed, is affected by local pressure areas for the pitot tube as well as the static ports, plus whatever plumbing you have in the airplane affects the fluid dynamic solution. The airspeed indicator is really a differential pressure gauge. Ram air into the pitot tube and static air pressure next to the aircraft. From that you can say, well, this pressure differential is equal to this airspeed. The static port, frankly, is the biggest problem because the pressure field changes around the airplane at various speeds, and you have to have flight tests to discover the installation errors. So, once you know the installation errors, you can compute a new airspeed called the calibration airspeed, CAS. And then once you have that speed, you can correct it for the compressibility of the air. But for most of us in GA flying, we don't go fast enough or high enough to have equivalent airspeed affect us. But you need equivalent airspeed to derive true airspeed. True airspeed is EAS adjusted for air density. True airspeed is the actual speed we fly through a given parcel of air. TAS, true airspeed, increases as we fly higher. In general aviation, we just assume that the differences between IAS, CAS, and EAS are negligible, and we go straight to true airspeed. With the advent, that's easy for you to say, of accurate GPS, we can cut out the tower flybys and reproduce the test results on our own, just by ourselves out there. So the simplest method is just to fly an upwind course and turn around and fly a downwind course. You can just record the speeds, average them, and determine a true airspeed. Your ground speed is your true airspeed, adjusted for winds. By flying the same course in opposite directions, you cancel out the winds, hopefully. The trouble is that errors propagate and interfere with your results, even if you don't know it. The wind is a variable field, and it's not the same at the beginning of your run as it is at the end. So that's one thing. A smart fellow in the past invented the triangular test path. By using an equilateral triangle and headings of 120 degrees apart, you cancel out the winds, the variation in winds, short-term instabilities in flying the profile, and what is more, you can reveal calibration errors in the equipment installed in your airplane. The Navy, by the way, they have to do this different. They do 4 courses with 90-degree turns. So, is your head spinning yet? Okay, if not, add to this that most lower-end glass panels that display true airspeed use the concept that your CAS, calibrated, is equivalent to your indicated. This is not always the case. It does not appear to me that flight testing was done in each aircraft type added to various approved model lists to determine what the CAS issues were. That's for certified. For experimental, well, it just depends on how you built it. Basically, that's up to you to figure, the owner-operator, what the errors are. Granted, the errors are not large, but pitot-static systems can easily be 5 knots or even 100 feet off, and that directly affects your true airspeed. Admittedly, I'm a bit of a geek, and I want to have a more precise knowledge of what's going on, and I didn't invent this stuff, but I did sleep at a Holiday Inn Express, so I traffic in complexity. It's fun, right? The spreadsheet that I use is to reduce my flight test data, tells me what the CAS errors are. It also helps cancel out the errors induced by different temperatures and density altitudes, so you can do it on different days. But, you don't really need to know this stuff. That's not that important. If you still want to do a triangular test path, and if you're interested, I've got a simple spreadsheet that I plagiarized from somebody else, from the experimental guys, that does a simple data reduction for a triangular test course. If anyone is interested, I can put it up on my website for you to download. Just let me know. In each one of the turns I'm making on this course, like I said, I can't walk, talk, and chew gum. I'm trying to do that steep turn at a constant altitude. Then I roll out of my heading, and I let the airspeed stabilize. Sometimes that takes about a minute or so. Then I record 6 to 12 data points. What I want is heading, temperature, indicated airspeed, and ground speed. All 3 courses, all about 10 miles each, which may be a bit overkill. But then I'm done, and I take all that data home to reduce the data. What I'm interested in today is baselining performance at a specific power setting. This airplane with this prop had a particular fuel flow. Real soon now, I'm going to change the prop and then I'm going to redo the test. I want to know what the difference is and take into account the errors that are inherent. And when I know that, then I can know what the delta is, and it's going to be related to the prop itself, only that. And I can know whether it's actual improvement or it just looks really cool. Later on, then I'm going to when I redo the engine, I will refly the whole profile to see how things change with the new engine, to see if that actually made a difference too. Trying to evaluate it instead of going, yeah, it feels really good.
100, call it 1,000 feet. We need 1,500 feet, so that's 2,500 feet. So we can do it. An aileron roll. And that's the end of our test track. So up we go. Unload, roll.
Well, now you know my dirty little secret. I'm a bit of a geek, but maybe not a really super serious flight test pilot. This is backyard flight testing. I want to get a fairly accurate picture, but I'm not going to go to extraordinary expense and detail because, it's just not that important. I want to get a good idea of what it is. And you can do it too. If you're interested, I'll send you the simplified Excel spreadsheet so you can do your 3 courses, and all you need is basically the course and the GPS heading. You can so you can figure out what winds are and all that, and then it'll figure out what your true airspeed is. And be honest with you, I actually did this speed test on 2 different days. First day was bumpy and very bumpy, and then the second day I did it. It was much smoother and 7 degrees cooler. And the interesting thing is I came out with then 0.2 knots for the average true airspeed. The true airspeed computation. So I have the hot results, the data reduction right offhand here. So 2,900 feet is what I did it at, the altitude I did it at. My indicated airspeed was 160 knots. The calibrated airspeed was 161. So that's pretty good. Just an error of 1 knot, pretty impressive. I've seen, on my Skywagon when I started, I did the same test the first time because I suspected I did have airspeed issues, and I think it was like 7 knots off. It was pretty considerable. I was able to tune that down a little bit. The altitude error is 14 feet, and then my true airspeed was 169 knots. Well, the first one was 169.3, the second one was 169.1, but that splitting the hair is a bit too fine for me, so 169 knots at 18 gallons an hour. Should be faster, shouldn't it? Well, anyway, old engine. I hope you enjoyed the video, and if you change the oil or something like that, or you're taking the airplane out of annual or major maintenance, do a short run for a leak check on the ground, check it and make sure nothing's untoward, and then go fly and just quick check through the systems to make sure everything's working right before you strike out on a long cross country, or especially at night or something like that. So just a quick maintenance check flight, functional check flight if you will, and then you'll be good to go. So hope you enjoyed the video, and does you some good, and thanks for watching. I appreciate that, and if you liked it, hit subscribe. I'll put the thing, it kind of looks like that right there, but it's going to be, where's it going to be? It's going to be down there. Hit the subscribe button and the bell if you want to get notifications. If you liked it, hit like. That helps me in the YouTube algorithm. If you don't like it, okay, fine. You don't like it. Tell me why you don't like it. Just don't throw the don't like spear at me. I'd like to know what I can do to get better. So I appreciate that. Also, I want to say thank you to my Patreon sponsors, my supporters. They're on Patreon. I'm going to put their names up right here. And I really appreciate y'all. And if you, anybody else wants to support the channel, I appreciate my sponsors right now. And if anybody else wants to support the channel, I'll put a link to the Patreon page right down below in the description. So, thanks for watching, and we'll see you next time on FlyWire. Click this link for the latest upload. Click this link for whatever YouTube thinks you ought to watch. Or you can click this link to subscribe. Thanks for watching.